15. It's not the second part. I don't feel is all that necessary for what you're going to be doing the rest of your life here. So, chemical equilibria is the concept for today. This is our last lecture before the exam on Friday. I just re-evaluated the exam and took out some questions and changed some questions, and I think it's a good test. So I hope that you will do well on it. We're moving on here to, oh, look at that, covers up some words. It's okay. Until now, we have assumed that, wow, I can hardly read with my awesome screen, that all chemical reactions are irreversible and only go forward. So in all the chemical reactions we've done so far, we take a couple of things and we mix them together and heat them up or stir them or shake them or give them some energy in some way, and all of a sudden there's a reaction. And we say these two things made this. Yes. Yeah. That reactions are irreversible and only go forward. Yep. But there's a great number of reactions out there that are reversible. That you can undo that reaction. You can push it backwards and get the reactants again from the products. So an example that comes to mind, I don't know, it was useful for those of us that live in a cold environment. I don't know if you guys have ever seen those hot packs that you could like take camping or something, and you pop a little thing in the pack and it gets hot, and you could put it in your socks, is what we used to do, or put it in your mittens or slip it inside pockets of your coat, and it helps warm you up. Those little heat packs are very, very useful, and the cool thing about them is that you can then reverse the chemical reaction. You can take a heat pack after it's spent and it's released its energy and warmed you for several hours. You can boil those things, and by adding a lot of heat back into the pack, you reverse the chemical reaction and you wind up with reactants again. And then you can pop and they start their chemical reaction one more time. So very cool. When I was backpacking through Europe in the winter, it got very cold in Scotland and Denmark and Finland, and we used those heat packs a lot, and they would keep us warm, and then we'd boil them at night when we were making our food, and be able to use them the next day. So it's pretty cool. That's a reversible reaction. Many reactions go both directions. You can go from reactants to products, and then you can take the products and get your reactants back. So you can back up the chemical reaction. And so in reversible reactions, reactants and products exist as mixtures. The reaction never goes all the way to completion. It goes some ways to completion, and then it like slows down and stops. But when it stops, there's still some reactants there that aren't spent. And then you can push the reaction point back towards reactants, towards products, depending on the environment of the reaction, what's going on around it. The relative speed of two reactions depends on many factors. So we have a reversible reaction that is going in both directions, and maybe it's going from reactants to products faster than it's going backwards from products to reactants. So the balance point is going to be further towards the products, but maybe it's the other way around. Maybe it takes a lot of work to go reactants to products, but it's pretty easy to go products to reactants. Then the balance point is going to be more towards the reactant side. So we're looking at that concept of a balance point between two opposing reaction directions here. Reversible reactions, reach a point of, I can barely read with all these dots. Reversible reactions reach a point of dynamic equilibrium, where forward and reverse reactions are going on at the same rate. So in that example I gave you of the heat pack will go almost all the way to completion, and that's why they choose that chemical reaction, because it lasts a long time and it goes a long ways. But there will come a point when the pack stops giving off heat and it reaches a dynamic equilibrium, and there is still forward reaction happening, but there's also backwards reaction that has started to happen. And there's a balance point where the two are happening at the same time, and so there's no net change in the mixture of reactants and products.
So you can heat up the pot again and it'll turn hot again, or it won't?
Yeah, you boil it, and that undoes the reaction and restores it to reactants, and you can use it again.
Oh, and just break it up again.
Yeah, yeah, it's pretty cool. So dynamic equilibrium is a place where forward and reverse reactions are going on at the same rate. We use the phrase dynamic equilibrium about lots of different things. You can talk about dynamic equilibrium of particles of fluids that are evaporating into the airspace above and condensing from the airspace back into the liquid. We talked about that a couple of weeks ago with vapor pressure. And that we use the same phrase, dynamic equilibrium there. You could talk about an osmotic system where water is osmosing across a membrane in one direction at the same rate that it's osmosing back the other direction, so that's dynamic equilibrium. This is not the first time you've seen that phrase. Here we're talking about chemical reactions, and we're talking about one reaction going one direction and the other direction going the other direction, and they're balanced. They're still both happening, but the speeds of the two mean that there's no net change. We have on average the same thing. Okay. The law of chemical equilibrium states that a reaction at dynamic equilibrium has a constant ratio of reactants to products. So when the reaction gets to dynamic equilibrium, the percentage of the mixture in that reaction vessel that is reactants and the percentage that is products remains constant. The reactions are both still happening, but because they're happening in both directions, the net ratio is the same, right? And so the relationship between the reactants and the products remains constant once a chemical reaction gets to dynamic equilibrium. So here's a picture. Here we have two graphs, and one is looking at reaction rate and one is looking at the amount of reactions, both of them as opposed to time. So looking at the rate one first, when we start the chemical reaction, the forward rate is initially much faster. It's going only forward in one direction. But the forward reaction starts to slow down as the reactants are used up and as the products are being produced. And once the products start to be produced, it's possible for the reaction to reverse. And the reaction rate of the reverse reaction starts to go faster as time goes on and more reactants are turning into products. So the forward rate tends to slow down over time, and the reverse rate tends to speed up over time. And then you'll get to this dynamic equilibrium where both reactions are happening at the same rate. Forward reaction is happening, reverse rate is happening, they're happening at the same rate. Okay, so that's dynamic equilibrium. You could look at that exact same situation as a concentration graph, and you could say there's initially a lot of reactants and very little products. And as time goes on, the reactants drop in concentration because they're being used up. But they don't go all the way to zero. And the products initially start off very small. But the products start to get made, and they eventually level off, and they don't go all the way up to the same concentration the reactants used to be, because they get to dynamic equilibrium, and there's no net change in the amounts anymore, because some reactants are still turning into products, but some products are going back into reactants. So at this place of dynamic equilibrium, there's no net change in the amount, because the reactants and the products are being made at the same amount of time. So again, no net change in the ratio of reactants and products. Just some more examples of that with actual chemical reactions. Here, if we had gaseous A turning into gaseous B, then over time, gaseous A concentrations drop and then level off, and that is that's the equilibrium point for the reactants. And the products increase and then level off, and that's the equilibrium equilibrium point for the products. And so we would see that here, the reaction point, or the dynamic equilibrium point, favors the products. There are more products than there are reactants at equilibrium. Here, we have the same kind of thing. We have something dropping off and then leveling out. And here we have something rising and leveling out. But we can see that in this one, it favors the reactants. There's many, many more reactants at equilibrium point than there is products. So here this reaction just went a little ways and then dropped off and leveled out and found dynamic equilibrium. Here the reaction went quite a ways, very close to completion before it leveled off and found dynamic equilibrium. So different reactions go different distances. Some reactions just kind of get started and then find dynamic equilibrium and like, yeah, we're done. We're going to not go any further. Other reactions go a lot further and then find dynamic equilibrium. And even reactions that go, quote unquote, all the way. If you were to very carefully look through the pile of stuff left over, you would probably still find some unreacted reactants. So even in reactions that go to completion, you would probably still find a little bit of reactant left over somewhere. And it's all about balance, right? In the dynamic equilibrium process, we're talking about the speed of reaction in one direction, at some point balancing the speed of reaction in the other direction. So you could think of it as like a teeter-totter or a seesaw. And some reactions are not very balanced. Some reactions go way more towards one side of the reaction than the other. So this would be an example of a reaction where it goes very far to completion and there's just a little bit of reactant left, and the equilibrium point is very far towards the product side. Or if the fat man were the reactants, then it would just barely begin to get started and then be done. Some reactions find a balance point in the middle, some reactions find a balance point not in the middle at all. Okay, so in this chemical reaction, we have a chemical reaction where there are reactants turning into products, and then products turning into reactants. And this is just showing you that it goes both directions. There are reactants turning into products at the same time that there are products turning into reactants. This is a equilibrium or a reversible reaction. Notice also the symbol that we use. We use an arrow, half an arrow going in each direction instead of just the regular yield sign that says all of this turns into all of this. We use a double arrow to show that the reaction is going to go in both directions. Okay, yay. I did? Oh, yay. Good times. So I guess that's easy. Reaction equilibrium constants. So when we were doing rate laws in chapter 14, and you came up with rate laws based on the concentration of reactants and how the rate responded, and we did the little exponent thing, we reviewed that yesterday. Now we're going to write rate laws for both the forward direction and for the reverse direction. And we're going to set them equal to each other at the equilibrium point, okay? And so the rate law going one way is equal to the rate law going the other way once they reach dynamic equilibrium. So this is pretty simple algebra here. I have a mathematical expression, constant times exponent, equals the constant times the concentration of the exponent on the other side. I'm going to set them equal to each other. And then I can come up with a new rate law. And I'm going to use, instead of just K, the reaction constant, I'm going to use KEQ for the equilibrium constant. And I'm going to say that KEQ measures whether the forward reaction or the reverse reaction is favored. So if my KEQ value is greater than 1, then it favors the forward reaction direction. The equilibrium point is going to be down the road towards the products. If my KEQ value is less than 1, then it favors the reverse reaction. The equilibrium point is going to be very close to the beginning of the reaction, up on the reactant side. So my KEQ is going to tell me how far does this reaction happen, right? So the thermodynamics chapter answered the question, will the reaction happen? The rate law chapter answered the question, how quickly will it happen? And this chapter answers the question, how far does it go? Does the reaction go all the way to completion? Does the reaction just get started and stop? Or does the reaction go almost all the way and stop, right? And so the KEQ value will tell you that. The greater than 1 favors the forward reaction, the less than 1 favors the reverse reaction. So let me show you some examples of this. Oh, yeah. There you go. So here's an example. If A plus B is in equilibrium with C plus D, okay, so that's my chemical reaction. I'm not bothering with what this actually is yet. But I have 2 reactants, A and B, and I react them together and I get 2 other reactants, C and D. And it's a reversible reaction, so I need the double arrow, right? Because A and B goes to C and D can also reverse and go to A and B. Once it reaches equilibrium, once the reaction settles, and it's going in both directions at the same time, then my forward reaction rate is going to be K times the concentration of A times the concentration of B. And maybe there's exponents up there. But for right now, we're going to keep it simple and just have first order reactions. And I'm going to use the little f next to the K to say the reaction in the forward direction, KF. Concentration of A times the concentration of B. And KR times the concentration of C times the concentration of D. So I've written a rate law for the forward direction, and I've written a rate law for the reverse direction. And so what I can do is say when they reach dynamic equilibrium, the reaction rate going in the forward direction equals the reaction rate going in the reverse direction. So I can take the rate law from the forward and I can set it equal to the rate law in the reverse. So K sub F times the concentration of A times the concentration of B equals K sub R times the concentration of C times the concentration of D. So you see what I've done here. Equilibrium rate, the forward and the reverse are happening at the same speed. So I can take the rate laws and I can set them equal to each other. Okay. Now through the magic of algebra, I can rearrange that equation. And so that K in the forward direction divided by K in the reverse direction is equal to the reverse rate loss, concentration of C times D, divided by the concentration of A times B. Now notice that when you do this with the algebra, you don't wind up with all of these on the top and all of these on the bottom. Because you have to divide and then divide, you actually wind up with the reverse on top next to the KF and the forward on the bottom next to the KR. So this might seem counterintuitive, but it's what happens when you divide the whole equation by K sub R. You wind up with the K sub R in the denominator, and then to get this over, you have to divide the whole equation by A and B, and then you get this over here. So that's the way the algebra comes out. But some people get tricked up by this. They think, why is the forward across from the A, from the C and D? That's just what happens with the algebraic rearrangement. Okay? And now I'm going to come up with a new value for K. K in the forward direction divided by K in the reverse direction gives me a new thing for K. I'm going to call it KEQ, my reaction constant at equilibrium. What is the reaction constant at equilibrium? It's the reverse rate law divided by the forward rate law. So the speed, yes dear? Hi.
Why is the J forward on the top and that one is on the bottom of the right part?
This is the same KF, KF, KR, KR.
The word, when it says reverse rate line, forward rate line, the forward is on
Like
the
the
bottom.
actual word.
The actual rate law, so this, the concentration things, this is the CD. That's the CD, which is the reverse. Not the constant. The constant is at the bottom, but the concentration relationship, that would have the exponents and all that kind of stuff. This is the reverse. This is CD going backwards. Where am I? This is CD going backwards towards AB. So it's the reverse rate law, the concentration relationships. And the forward rate law is the concentration relationship. So KEQ is my new expression for KF over KR. I'm changing these into, I'm going to do this division and say that's KEQ. And KEQ is then equal to whatever my reverse rate law, the concentration relationships are, divided by my concentration relationships in the forward direction. Okay? So you wind up with some number, which is the division of the reverse rate law divided by the forward rate law. And that will be what KEQ is. And again, if it's greater than 1, then what you're saying is that it's going to favor the products. And if it's less than 1, then it's going to favor the reactants. Okay. If all the substances are not in the same phase, any undissolved solids or solvents have a concentration of 1, and so we don't include them. And this comes into play when we're looking at reactions where something settles out. You mix 2 liquids together, and you get a solid precipitate that settles. Well, that solid precipitate is not going to interact with the liquid above it because it's all in a big clumpy crystal, and it can't interact in the middle of its crystal with the liquid around it. Or in a gaseous situation, you mix something, mix liquids together, and a gas bubbles out. Well, that gas is no longer going to react with the situation, with what's left in it. So when we have something like this, I have, I'm covering up another word here. I have the breaking down of silver chloride, and I get aqueous silver and aqueous chlorine gas. When this stuff breaks apart, it's all in solution. But when it goes backwards, we're going to wind up with a solid that's going to chunk out and go to the bottom of the beaker or the test tube where this is going on in the reaction vessel. And so the stuff that's in the reactant side, the AB, this thing, is solid, and it's in a different phase than the liquid part of the reaction. So I can just put 1 there, and it doesn't count. The division, it winds up not mattering, right? Because when you multiply divide by 1, the answer is the same. So the anything that is in a different phase, we get to ignore, which makes the math a little bit simpler. Okay, I think I have some examples to go through here. Oh, and this is just showing you why. Because in a reaction here where a crystal precipitate is formed, this first layer of stuff may react with the solution around it, but all of these solid parts of the crystal underneath are not going to come into contact with the reaction out here, and so it's not going to contribute to the reaction equilibrium. Okay, so only things on the surface will react. So we get to basically ignore the majority of this solid. Okay, so let's do an example together. For the reaction, N2, nitrogen gas, plus 3H2, gas. So I have hydrogen gas reacting with nitrogen gas. That reaction produces ammonia, 2NH3, again as a gas. And that's in equilibrium. So some of the ammonia is going back and decomposing back into nitrogen and hydrogen. Determine the value of KEQ given the data. So my leprosy screen, it's kind of hard to see, but the concentration of nitrogen is 0.05 molar. The concentration of hydrogen gas is 0.05 molar. And the concentration of ammonia is 0.5 molar. So this is 10 times more concentrated than the concentration of the reactants. And this is the concentration of things at equilibrium. We allow the reaction to go until it looks like it stops, until it reaches the balance point, and things are happening in both directions at the same time. And so we want to know what's the value of KEQ. So KEQ is the reverse rate law divided by the forward rate law. So KEQ is the concentration of ammonia, concentration of the products, divided by the concentration of the reactants. And here my coefficient of 3 became a third power, and my coefficient of 2 became a second power. Okay? So concentration of ammonia is, maybe that's not 0.5, maybe that's 50. That's 50. Okay. So concentration of ammonia is 50 squared divided by the concentration of nitrogen and hydrogen, and the hydrogen is cubed. So I just put in my data at equilibrium point and do a little math. 50 squared is 2,500. 0.05 comes straight across, and then 0.05 to the third power is 0.000125. Multiply all that across, and then divide. And I wind up with a very, very large number. So KEQ is 400 million. It's a huge number. And remember, my test point is this number bigger than or less than 1? Is that bigger than or less than 1? Bigger by a lot. So did this reaction favor going forward or going backward? Going forward by a lot. And you can see that at the concentration at the equilibrium point. Molarity of 50, molarity of 0.05, molarity of 0.05. And so this reaction went almost all the way to done before it found an equilibrium point and stopped, right? So a very large value for KEQ means this reaction went towards completion before it stopped. Anything greater than 1 favors the products. The higher the number, the more it favors them. This reaction is underneath my picture in red. There you go. Essentially goes forward to completion. It goes almost all the way to done. Okay. So that's the kind of stuff you're going to be doing, is looking at the concentration at equilibrium point and doing a little bit of simple division. I'm not kidding. There's a little more. Le Chatelier's principle. When a system at dynamic equilibrium is stressed, the point of equilibrium will move to relieve the stress. And what do we mean by that? We take a reaction, we let it settle, we let it find dynamic equilibrium, we let it find the point where it's balanced. When a system at dynamic equilibrium is stressed, the point of equilibrium will move to relieve the stress. So we take something, we let it settle, we let it find the equilibrium point, and then we mess with it. we change the concentration, or we add more reactant, or we add more product, or we change the temperature, or we change the presence of a catalyst, or something of that nature. We can watch the equilibrium move. Now, some things will impact the equilibrium point and some things will not. Generally speaking, adding a catalyst or changing concentrations doesn't change the value of KEQ, because you'll just add more reactant. That reactant will get used up and the balance point will reestablish. And then if we were to measure the concentrations and do the math again, we get the same value for KEQ, because the reactions will still be going forward or backward at the same speed that they were going before. You'll get a very short-term fluctuation in the value for KEQ, but once you let it settle again, then it'll be the same thing that it was. But if we change pressure or heat, then we can actually get a different value for KEQ, because quite often a forward reaction might be exothermic, and the reverse reaction may be endothermic. And so if I add more heat, then I'm able to push it more in the reverse direction. Or if I put the whole reaction in the fridge, then I could get it to go more towards completion. And so changing the amount of available thermal energy will actually change my value for KEQ and change the point at which the equilibrium is set up. I can also do that with pressure, which is strange, and you think, why does pressure change where the dynamic equilibrium settles? But you have the same amount of mass in a chemical reaction. You can always find the same amount of mass, right? The law of conservation of mass. But as things get rearranged, they may take up more or less space than they used to. You mix two liquids together and a gas comes out. Well, that gas takes up a lot more room than the liquids used to. Or you mix two liquids together and a solid settles out, and maybe the whole thing gets a little bit smaller. And so the volume of reactants and products is not the same. That's not conserved. So by adding pressure, I can force something into the smallest space that it can take up, which may be one of the reactants or the products. So sometimes you can force KEQ to change by adding pressure. Sometimes you can force KEQ to change by adding heat or taking it away. So Le Chatelier's principle just says that if you have a reaction at dynamic equilibrium, you can futz with it and get that equilibrium point to change a little bit. Some things don't affect it. Concentration, catalysts don't affect it. Other things, heat and pressure, do. And so that is something that you'll be able to see in a lab. Okay? This is actually the point of the lab that we're going to be doing tomorrow. So if I have here hydrogen plus nitrogen, and I'm going to be making ammonia out of hydrogen and nitrogen. In the forward direction, hydrogen and nitrogen on their own take up more space. And in the reverse direction, going forward, hydrogen and nitrogen take up more space than the products, than ammonia. Ammonia is more dense. And going backward, it's going to expand because the ammonia is going to break apart and the hydrogen and nitrogen take up more space than the ammonia does. So nitrogen and hydrogen combine to form ammonia. As they do so, the gas pressure is reduced and heat is given out. According to Le Chatelier's principle, to make the reaction proceed left to right, high pressures and low temperature are needed. So if when I go forward, I take up less space than if I were to increase the pressure on that reaction and put that reaction in some kind of chamber where I can ramp up the pressure, I'm going to make the reverse reaction very unfavorable. And it's going to want to squeeze these things down into their products. And it's going to push the equilibrium point more towards the product. Also, nitrogen plus hydrogen giving ammonia releases heat. And it takes that heat to go backwards. So if I were to make this reaction happen in a refrigerated environment, then I'm going to draw that heat away from the reaction as it's happening and rob the reverse direction of energy to go backwards. So if I want to drive the reaction towards the product side, I'm going to crank up the pressure and put it in the fridge. And then I will wind up pushing the reaction to completion instead of letting it find equilibrium partway through. Okay? And I could also do this exact same idea if I wanted to take ammonia and I wanted to break it up into nitrogen and hydrogen gas. I could take that ammonia, I could set it in a reaction chamber, and I could suck out all the air above it. I could put it in the vacuum. And then I could heat that thing up. And then I would be saying, hey, let's take up as little space as possible and let's add heat to it, and I would drive the reaction back towards reactants. So you can change the point of equilibrium by changing pressure and temperature. That's Le Chatelier's principle. And that is it. What questions do you have?